supercapacitors, the actual device, and how we can evaluate the performance of the supercapacitors, and after getting the data, how we can analyze this. So, and what are the applications? I mean, the main applications where the supercapacitor really used. So this is what I'm going to cover next 50 to 1 hour. And then if you have any queries, please put your comments on the chat. And if you have any further queries you want to convey or you need to discuss with me, you can email through muraganathan@cres.in. So this is official that email ID. Okay. So my talk completely going to cover so basically that what is the difference between the conventional and electrochemical capacitors, and then the characteristics of the electrochemical capacitors, so which we need to keep in mind while testing the supercapacitors, and what kind of electrodes and electrolytes which is essential for supercapacitor for getting that good performance. And of course, as I mentioned, the testing analysis of the 3-electrode system. I mentioned the 3-electrode system. That's the reason where we failed to, explain when you make it as a manuscript or in the case of reports. I used to find a lot of mistakes. It doesn't mean to, so I'm comparing to anyone. So here, this means I'm going to give certain fundamental aspects. How we can describe, how we should describe the performance of the materials based on the 3-electrode system, as well as how we can fabricate the portable supercapacitors, which means the actual device, and then applications of supercapacitors. Of course, we know energy is everywhere. So we are using, right now we are getting the energy from the incineration plant, thermal incineration plant, and nuclear power sources and other things. But of course, the fuel of fossil fuels play a major role, giving that in electric vehicles as resources for electric vehicles and other many applications. But the problem, as we know, right, that fossil fuels as well as, of course, that shortage of that in the future, that pollution, that carbon emissions which comes from the fossil fuels usage are the major drawbacks. So that alternative resources are wind, hydro, and of course the solar. So in that case, so we may have that wind and solar and hydro. So we cannot get these are all intermittent for resources. So we cannot use it at all times. Right, so we may need where we have the problem is, so we cannot directly connect a grid, but if there is no power generation in that unit, we can't that grid connection, or in the peak powers we cannot supply that requirements. So that case, so we may need a suitable energy storage devices. Of course, the supercapacitors may not be the right choice for using the grid applications. But this is one of the storage applications. So of course nowadays we are using the lithium-ion batteries and electrochemical energy storage devices, particularly lithium-ion battery supercapacitors. And in this case of solar and wind to grid connections, we may use high energy storage, likely redox flow batteries is being attracting much more in recent days. Because that energy and power we can independently vary, and we can store much energy in terms of a gigawatt hour. So using that redox flow battery system. Of course, I'm going to cover here about the electrochemical energy storages, particularly so supercapacitors. Then, what is the importance of the electrochemical supercapacitors? Right. So see here in the left-hand side, so that this is nothing but of a Ragon plot, basically, which can describe the information about the energy and power density of the devices. Say, for example, in the left-hand side, so the capacitors, supercapacitors, and the batteries and the fuel cells. So here, look at here that the capacitors, so normal conventional capacitor can have a high power, but their energy density is very less. So we know that basically that the difference between the energy and the power, right? So if I have 100 kg, there is a weight. So if I can be able to lift the 100 kg, that is nothing but of a power. How long I can carry that 100 kg, that is nothing but of energy. So that's what that say simply if you are interested in cricket. So if you imagine that the test match as well as the 2020 cricket match, if you want to play the 2020, you need a more power. If you wanted to play the test matches, you need a high energy, like that. You can imagine whatever you wish, so that way, so power and the energy relation. So here, that conventional capacitors have a high energy, high power, but they fail to deliver that energy, that power for a long time. But in the case of supercapacitors, so you see in the case of batteries, you look at here, they can able to deliver high energy, but the power density is very, very less when compared to the conventional capacitors. But in the fuel cell, it is a different scenario, that is the energy conversion device. So I don't want to go in detail about the fuel cells. So here, look at this supercapacitor, which somehow managed to give the high power as like as a, I mean, not as like exactly as the capacitors, but a supercapacitor can able to give still it can able to deliver high power, but also it can able to deliver the energy density. So which is I mean plays in between the capacitors as well as the batteries. In this case, so that what is the motto and what is the aim of the working in the supercapacitor? They are always trying to enhance the energy density, so somehow extending that energy density as well as somehow extending the power density of the device. That you can play around using some different materials, different configurations of the device. Of course, different electrolytes, whatever that is, different engineering aspects. You can play around that, and then you can get you can balancely getting that power and the energy density. Once you can able to cover this power and the energy, so sometimes possibly it can able to replace the batteries as well. If it is performed well, it can able to deliver the high energy. This is what people are looking, and people are continuously working on various aspects for enhancing the energy density of the supercapacitor. Look at here that the conventional capacitors always deliver the power in milliseconds. In fact, in electrical circuits which we used in normal any electrical circuits, that is a conventional capacitors likely based on the dielectrics, they can deliver the power in fact in very short range in terms of microseconds. In fact, even here it is mentioned millisecond. In fact, it is a microseconds. And if you look at the electrochemical capacitors, what I'm going to briefly explain. So here, the electrochemical capacitor can deliver the power, the same power nearly 10 to the power, which means that 1 kilowatt hour, 1 kilowatt per kg. So nearly about in terms of seconds, or of course in terms of minutes. But in the case of lithium-ion batteries as well as the lithium primary batteries, so here that the energy density will be very high and the power density is poor. So the basic difference between the power, the batteries and supercapacitor based on the power and energy relation. So electrochemical capacitors, conventional capacitor, they can able to deliver much power when compared to batteries. At the same time, the batteries can deliver much energy than the supercapacitors. And then of course, so now the importance of the electrochemical supercapacitor or electrochemical energy storages. So look at here. So this is that left-hand side. That the first one. That is the very first electric car, which was in 1989. Of course, there is a lead-acid battery-based cars who were driven by someone. And of course, after 100 years later, so this is the Tesla's hybrid car. Recently, a few years ago, they launched, and it is on road right now. And of course, we are always looking for modernization. Of course, there are some towns in each and every stages. So beyond that, health issues or medical, crisis. So we always when looking for modernization as well as for better technology outcomes. So that in such a case, you look at here that left side, that how that electric cars it is modernized, and what we are having now based on the developments in the electrochemical energy storage devices. Of course, in the right hand side, you see the cellular phone. So this is a battery where what they used for that the rubber phone early stage, of course, 100 years late before. And now we are look at that the bottom one, how it is flexible. That is, of course, the flexibility and other things. It is mainly based on the energy source which used in that power that systems. If you are if you can able to make that as much as flexible that resource, the energy storage device, so you can able to make it as a more flexible. So this is what the scenario. So this is what the importance of electrochemical energy storage systems. So we can be able to make more compact and economical and eco-friendly to save our environment as well. Of course, basically, as I mentioned earlier, there is no difference. There are not only the difference that the energy and power, there are a huge difference between the lithium battery and the supercapacitor. Of course, that the gravimetric energy lies between that lithium battery 100 to 265 watt hour per kg, but in the practical case it is nearly 170, 180 watt hour per kg. But in the supercapacitors, so gravimetric means if you are getting that energy based on your weight of your material. So here that is a 4 to 10 watt hour per kg. And of course, the power density, as I mentioned, the supercapacitor giving high power range. And the voltage of the cell, of course, in using the lithium battery nowadays, we can have a nearly 4.2 volt or 4 volt, 4.5 volt cells using it. That depends on the configuration of the anode and the cathode materials. Of course, in the supercapacitor, that depends upon that electrolyte system which we used. If you're using the aqueous electrolyte system, you can limit the potential less than 2 volt. If it is organic, you can go more than 2 volt. Of course, that is the ESR. So everyone should know about the ESR, electrical series resistance. I mean, that electrical series resistance of the device. Say, for a battery, you don't want to bother about the electrical series resistance, ESR value. But in supercapacitor, it is a very, very important factor because this will controlling or this will affect the power factor of the supercapacitor. If you need a more power, so that electrochemical capacitor should have, I mean, that ESR should be very, very less, in fact, less than 100 milliohm. Of course, the efficiency each and every cycle, the supercapacitor have a 99% of efficiency, which means how much you charge, that much you can able to deliver. You can get a train from the device. But in the battery, of course, after this 90, 75% and all, after the second cycle, in fact, the first cycle of any secondary batteries will be the huge problem. That is, the Coulomb efficiency in the first cycle will be very, very less. So nearly it will be nearly 60%. After that, probably you can get nearly the charge, I mean, the efficiency nearly 80 to 90%. Of course, the cyclability, if you're using the secondary batteries in the mobile phones, so what we have, so probably 300 times, 500 times the charge and the discharge, which means you can charge it and completely discharge it. That is the one cycle life, so of the batteries. So which means you can able to 500 times and 1,000 times you can able to fully charge and discharge. This is what after every 1 year or 2 years that your mobile phone batteries or wherever using that secondary batteries, their lifetime of the battery is very less. But in the case of supercapacitors, so their lifetime will be, we can't define it, probably it is more than 1 lakh cycles people are tested so far in the literature. Of course, that lifetime. And another thing is the self-discharge. The major problem in supercapacitor is the self-discharge because of the mechanisms, the charge storage mechanism involved. The self-discharge is unavoidable in supercapacitor. Of course, people are trying to work to avoid the self-discharge. Which means if you charge your battery, what will happen? So if you leave it that the battery charge the battery for next after 3 days, if you come and look at that your battery system, what will happen? It will still have the battery charging. At charge it is probably certain percentage only left, and nearly 80% or 70% of the battery charge will be still. But in the case of supercapacitor, if you charge it and if you leave it for 3 days without any disturbance, if you look at that potential of the charge, I mean the state of charge of the supercapacitor, it will be nearly 5% or less than that. Which means it's a self-discharge. The charge, self-discharge will be very high for supercapacitor. It is a major drawback of the supercapacitor, of course. And the operating temperature, it is basically based on what type of electrolyte which you are using. Probably in that case of secondary battery, mostly people are using that organic electrolytes because of that. I mean, that's why the operating temperature is 55 degrees Celsius. But in the case of supercapacitors, we can use aqueous to organic or ionic liquids, so that why the operating temperature is also possible. And next thing, the deep discharging problem. Of course, the lithium batteries. So if you deeply discharge every time, sometimes there is a memory loss. So what will happen? You can't fully charge it again, and the battery life goes down because the lithium battery, not only the lithium battery, it is the secondary batteries. That mechanism is really dependent on the structure of the electrode materials, and the mechanism involved it also affects the deep discharge. But in the case of supercapacitor, no matter you can charge it to zero, then you can boost up again the same potential in that supercapacitor. Of course, supercapacitor had the high power, then overloading problem would not be the issue. And the risk of explosion, it is possible in supercapacitor also if you are using organic electrolyte. But in the case of aqueous based system, you can minimize the risk of that supercapacitor system. Of course, the cost, somehow the supercapacitor side, the cost is somehow increased because of the processing of the systems. But still now we can able to minimize and we can get the less power or less energy when using the aqueous-based supercapacitors. I'll explain how we can minimize the cost of the systems. And basically, when you use the battery and supercapacitor symbol, so this is what the battery symbol as well as the supercapacitor. If it is a variable, you can just you can see that somehow that curvature-based symbol in the supercapacitors. So basically, so the battery nothing but of this is nothing but of the half cell. This is a one cell and this is another cell. So if you define the battery means this is a combination of the number of cells. So which means one half cell and then another half cell. So which means if the one or more cells connected, which is nothing but of a battery. So this is the basic things which is in electrochemistry. Of course, now come to the point in the supercapacitor part. So what is the basic difference between the conventional capacitors as well as the supercapacitors? So in this case, so what will happen? So in the case of conventional capacitor, so basically the conventional capacitor, if you have the two metallic plates separated in a dielectric medium by some dielectric medium, if you apply the potential, there will be charge separation, which means the charge is induced on the metallic plate by electrostatic induction, right? Which means the charge is stored electrostatically under the conventional capacitor. Of course, in the EDLC also that absorption disruption, that is electrostatically charges are stored. There are some other mechanism also involved in the supercapacitors. So look at here. So here that is the capacity of the conventional capacitor is based on that C equal to A epsilon divided by D, which means the distance between the charge plate. Of course, the nature of the dielectric medium as well as the dielectric constant. It's all on the area of the plate all playing the role in determining the capacitance of the conventional capacitors. But in the case of electrochemical capacitors, so basically the electrodes can immerse in the floating electrolyte. So where the potential applied, so that solvent ions in that electrolyte system, so that can be absorbed on the electrode surfaces, it can form a double layer, so called as electrochemical capacitors. So in the case of the major difference between the conventional and the electrochemical capacitors, the electrochemical capacitors have a high capacitance because of the electrodes nature, and then the pore structure of the electrodes and the electric double layer formation. Of course, in the conventional also there is electric double layer formation. And another thing that the other advantage is the high efficiency as well as the long lifetime. Because of that we can control the cycle life as well as the efficiency based on that. I mean, by choosing the right, by adapting proper electrolyte, of course, that electrolyte should have a high conductivity in the case. And based on the mechanism involved, we can classify the capacitors, particularly the conventional capacitors and electrochemical capacitors. Look at here, the electrolytic capacitors and the non-electrolytic capacitors mostly used in the electrical circuits. So which means that the electrolytic capacitor, basically aluminum on the handle. Everyone may be, we may have, frequently look at, find out the kind of capacitors in most of the electric circuits. So of course, nowadays that, it is rare to see maybe the CRT based picture tubes based television systems we may use to many capacitors like this. This kind of capacitor is called electrolytic capacitors, where the electrolytic system are aluminum and tantalum. And the non-electrolytic system, so it may be made up of a dielectric material and a polymer film and a ceramic may be used for separating the metallic plate. So maybe this is a kind of a ceramic and a dielectric capacitors. And of course, here I am going to concentrate only on these electrochemical capacitors. That electrochemical capacitors can be further classified into EDLC capacitors and pseudo capacitor and asymmetric and hybrid. So basically, these are all the two types: EDLC, electric double layer capacitor, and pseudo capacitor are the basic two types of electrochemical capacitors. If based on the combination of these two types of the capacitor, we can call it as an asymmetric capacitor. Say for example, if you use one pseudo capacitor material and EDLC combination, then we can call it as an asymmetric capacitor. If you used instead of pseudo capacitor material, if you use one battery type, either anode material or cathode material, in combination with the electric double layer capacitor materials, that is nothing but of a hybrid battery type with hybrid capacitors. So basically, there are types: electric double layer capacitor and pseudo capacitor, asymmetric capacitor, and hybrid capacitors. In the case of electrochemical, so of course, so this is kind of electrochemical capacitor, which is the very first electrochemical capacitor, which is patented by the Becker. I mean, who is the inventor of the electrochemical capacitor. I will give the text later. And so, of course, there is a phenomenon electric double layer formation. So, how I mean, we can define and how people get that information from the whether the double layer is formed or not, or something like that. So that phenomena absorption disruption occurred while immerse that metal plate inside that electrolyte medium, which means electrolyte means, as you know, right, those are ions, solid ions in that medium. So here, in the case of Helmholtz, so I mean, Helmholtz person who in 1853 he started, and he is the one to do the proper analysis and give the model for exactly for the WA formation, which means what will happen when a metallic plate immerses in that liquid solution, which means that electrolyte solution. So at the moment when you dip that metal plate, when you apply the potential, what will happen? There is a formation of there is a formation of electric charges of the metallic surface, which means so the electrolytic ions. So based on the potential applied, so here based on the potential of the electrodes, if it is a negatively charged, so what will happen that the positive charges gets to accumulate towards the surface of that metallic plate within that electrolyte system. So what happened? So that of course in the case of the Helmholtz, that charge separation at the electrolyte interface is not compact. In fact, when Helmholtz derived that AA formation model. So later people started and they said that this layer is a more compact layer, but that charge separation distance is not exactly what Helmholtz is derived. Basically, Helmholtz what defined. So when you immerse the metallic plate inside the solution, the double layer is formed. At the same time, that the double layer separation is in the order of less than 10 nanometer, 10 Armstrong unit. So which means the charges gets separated at the interface. So which means the double layer is formed. So basically, if you use any metallic plate, if you immerse in the electrolyte medium, so that the double layer charge, the charge separation means the number of charge carries to that electrode interface is nearly 10 to 20 millifarad per centimeter squared. If you use centimeter squared of that electrode materials inside. Of course, so you see here, so at the electrode interface only that double layer will be more compact. But with respect to the distance, so when increasing the distance from the double layer, what will happen to that? Which is nothing but of a diffuser layer. So where the potential may not be constant, or that the potential will be from the electrode distance. If you goes from the electrode, if you go so far away, so that potential also get less. So this is what Helmholtz defined using his model, how the double layer formed when if you immerse inside the metal. So this is the origin for making the electric double layer capacitors, electrochemical double layer formation capacitor. We later on, based on the Helmholtz layer and the GC model also established 1910 and 1913. So where the ions which we dissolve inside that electrolytic medium, not only as an anion and a cation, so they are getting solvated ions, which means that that molecules get hydrated, and that hydrated molecules can be accumulated on the electrode surface, and even that electrode the charge layers formed on the electrode surface is more compact, and that the charge layer is mainly depends on what type of metals is inserted inside the electrolyte medium and the concentration of the electrolyte. Of course, the double layer capacity also depends on the applied potential. So in the case of GC model, so which means that the double layer formation of the charge storage is mainly defined by the metallic plate, what type of metallic plate, and that applied potential, as well as by that the electrolytic concentration which we used. Of course, it is a pH related also, that I will explain later. So this is what the different types of model which was established before finding that better, the double layer formation, the electric double layer capacitors. Right now, on based on later GC model, Devanathan and Muller-Wolber model also, That's the DBA model basically. People say, I mean, they used right now we have of course what are the model we used is based on the DBA model. They were not in Muller and Wolmer model. So basically that also included the diffusion process as well as the pseudo capacity process, which are used in, I mean, which have happened at the electrolyte interface. Of course. So these are all the model. Based on that models, we are going to fabricate the electrochemical capacitors. So what kind of materials that can be used for electric and electrochemical supercapacitors? So in the case of electrochemical capacitor, the electric double layers capacitors, which means that the physical phenomena only happen that the charge carriers, that the charge storage can be happened only due to the absorption and the desorption. There won't be any redox process. So which means in the case of pseudo capacitor, there is the chances of a complete redox process, which means the oxidation and reduction will happen. The charge storage is due to the oxidation and redox process. Of course, the metal oxides and the conducting polymers mostly call it as pseudo capacitor materials. And in case of hybrid capacitors, which means so that the composite materials or battery type materials can be used with the hybrid capacitors. But on the other hand, what kind of electrolytes can be used? Of course, that as I mentioned earlier, that electrolytes can is the major role, play the major role, which can able to determine your cell potential. So there are many cases of many different types of electrolytes are used. Of course, electrolyte, organic electrolyte, ionic liquids, or solid state, which is depends on your cell configuration, what type of cell you need. If you needed the flexibility in your cell configuration, you should go with that solid state, or solid state or solid gel or gel based electrolytes. So in the case of organic electrolyte, of course, there are commercial people. In fact, that Maxwell, whatever we are saying, that Maxwell test people are using either acetonitrile or other organic electrolyte. Normally, battery electrolyte can be used for fabricating the supercapacitors. So I always prefer the aqueous electrolyte. So using that aqueous electrolyte, I always try to get maximum energy density. Of course, I mentioned earlier that so everyone's motto is to enhance the energy density of the supercapacitors. So of course, if you have a high organic electrolyte, so if you're using the organic electrolyte, you can extend your voltage window of the device. By the way, the energy density which is equal to half CV squared. So the potential window, the voltage window of your system is enhanced. Then you can increase the energy density. Of course, in the case of but the problem with this organic electrolyte is that its charge storage is very less when compared to the aqueous electrolyte. So I always prefer the aqueous electrolyte because of that wide operation temperature, and the self discharge also very less for the aqueous capacitors. And another thing that the conductivity of aqueous electrolyte also very high, and it can give a high capacity for VDC capacitors. That's why I always prefer the aqueous based electrolytes so for my studies, of course. So what kind of materials can be used? As I mentioned, that all carbonization materials can be used to activate, the ADLC materials. But that depends on the material's nature and the physical phenomena, physical parameter associated with the active materials, that the charge storage will be varied. Say for example, if you use activated carbon, if you use a normal conductive carbon, so basically the activated carbon can have a high capacitance, high charge storage phenomena, charge storage behavior because of that physical properties. Likely that activated carbon can have a large surface area with high porosity. And of course, activated carbon have a high wettability when compared to the normal conductive carbon. Say for example, so if you have two carbon materials, likely if you purchase curare or some other numeric kind of activated carbon which is commercially available, so if you have something like a super P or some other conducting carbons, say like you can use it as a CNT, carbon additives or multi-wall single-wall carbon additives. You can easily check the wettability. So activated carbon always have a better wettability. That is very important when you use it in the electrolyte interface. That wettability is a very important factor. And of course, the high electrical conductivity. Another thing that activated carbon always have a low conductivity when compared to the super P or some other conductivity, so it is CNT materials. So which means so we should always try to enhance the conductivity of activated carbon, since the activated carbon only can contribute much charge storage capacity. So in that conductivity of the activated carbon can be enhanced while preparing the electrode material. That I will tell you later. And of course, that conductivity, that is that material should have a long cycle stability. So, which means, as I mentioned, the supercapacitor should have a high long-term cyclability, so more than 50,000 or 1 lakh cycles, even more than that. So another thing that the force size and the force distribution of the particle diameters, everything is an important factor. Of course, these are all play the major role in determining the specific charge storage in the AA capacitors. Say, for example, how if it is a more porous or high surface area, so you look at here, the charge storages will be enhanced in the activated carbon. But in the normal conducting carbon, the surface area will be very less, only that the conductivity will be very high. The reason for the less conductivity of the activated carbon is due to the functional groups which is present in that activated carbon, which means that the OH and as it is, I mean the COO group or ketone groups or OH groups will be very high value activation. That is that can be controlled based on that activation process. If you need if you need any information about the activation of carbon materials or how to and derive the activated carbons from biochars, there are a number of literatures, so you can just Google it and find there are simple methods using pyrolysis process. You can have a high surface area, high porous active materials. And of course, as I mentioned, that the porosity is a very important factor which can determine the surface charge storages in the electrode EDMC materials. Say, for example, that pore size will be varied according to the pore size. So we can classify the activated carbons pore size distribution. So if it is a microporous, means it is less than nanometer size. So look at here, there is a micropores. So nearly less than 1 nanometer size of the porous is here. And then mesoporous means the pore size should be 2 to 50 nanometer, and the macropores means that the pore size should be higher than the 50 nanometer. Of course, the longer activation time or higher temperature leads to, as I mentioned, the activated carbons are always prepared using the pyrolysis process. If you use that temperature, if you are prepared the activated carbon at 800 degree, if you use the 2 hour instead of 2 hour activation time, if you use for 3 hours, the property of the material will be entirely different. So we can optimize that. If you say, for example, if you will find any bio waste from the nature, if you are going to activate that sample using the pyrolysis process, so that physical phenomena like pores distribution, surface area can be controlled by the activating agent. Activating agent, which kind of materials that we used for activation, likely potassium hydroxide, some of the activating agent I will tell you. So for potassium hydroxide, sodium hydroxide, zinc chloride. So you can see the difference when you use the different activation agent. Say, for example, if you use a zinc chloride, you can have a controlled pore. At the same time, you have to optimize the activation time, likely 2 hours, 4 hours, 6 hours at a particular temperature. Or you can fix the time and you can vary the temperature. If you play around that pyrolysis and the external condition, you can have a variety of properties of this carbonation, EDLC based, the carbon-based materials. Of course, as I mentioned, if you have a double layer formation for such materials, carbon materials. So in organic electrolyte, they have 100 to 100 farad per gram in organic electrolytes. But in the case of aqueous electrolyte, still you can get 150 to 300 farad per gram, which means that 20 millivolt per second or 1 ampere per gram when you testing that when you test that materials. So that's why I always prefer the aqueous electrolyte. Say, for example, so if I use the carbonization materials, I use, if you use different materials like 2 molar H2SO4 and 0.1 molar of LiClO4 and ionic liquid, look at here, there are 2 times higher capacity we have achieved for that, not my one. So it is high capacity, that carbon materials will high capacity 2 times than the other aqueous systems. Of course, when you use ionic and organic electrolyte, the potential window will be very high. But instead of enhancing the potential window, sometimes you can enhance the capacity so that lifetime of your electrode material will be very high. So that's why, so that in aqueous medium, so we always support the aqueous medium that the capacitance will be very high when you use the aqueous based supercapacitors. Of course, it is a pH dependent, so it is depend on that electrolyte nature, which means that if it is acidic, that potential window of your electrode materials will be different. If it is a base, which means if you are using 2 molar KOH or 1 molar sodium hydroxide, the potential window will be different. Or if you use a neutral electrolyte, it will be entirely different. You can see that different mechanism also is the EDLC, the carbon materials, which means it is a pH dependent as well. Of course, this is what the first electric double layer capacitor based on the carbon-based blocks, which was invented by Becker. So this is patented in 1957. Of course, after 50 years later, only that the commercial capacitors, electrical capacitors, comes to the market. Okay, that's all about the EDLC capacitor. So EDLC, all the carbonization materials can be used as a can have a electric double layer formation, which means the charge storage is mainly based on the physical phenomena absorption and disruption. Some cases there will be a diffusion, the possibilities that depends on the pore size. Say for example, basically if you have activated carbon the H2SO4, you can see some of the you can see some hump between 0.5 to 0.4, which means that the proton gets accumulated and that porous nature of the carbon materials. So which means in the electric double layer, most of the carbon materials can have an electric double layer formation mechanism. Some cases that depends on the pore size, there will be a diffusion process that you can visibly see in the characteristics. And in the case of pseudo-capacitive materials, you see, look at here, we are trying manganese oxide always as a better pseudo-capacitive materials. But you look at here, when you look at the charge curve, it seems like a double layer formation. But basically, it is a surface-based reaction, so it have a pseudo-capacitive mechanism. And at the same time, it also have a double layer. So it is always what we have in real time. So that is a mixed process. Maybe sometimes it is the double layer in the pseudo-capacitive nature. The double layer may probably negligible, but there will be a double layer formation. So in the case of double layer also, there will be a diffusion process or a pseudo behavior, but that is negligible. Say for example, the transfer metal oxides, nitrates, conducting polymers can be used as a pseudo-capacitive materials. So I will tell you how it will look like, how we can identify whether this material is electric double layer or pseudo-capacitive material. I will tell you later how we can define such scenarios. And these are all some of the double layer material, the pseudo-capacitive materials frequently used in literatures. And of course, that apart from that, transfer metal oxides or transfer nitrites or metal hydroxides. So here that the polymer, the conducting polymers, likely polypyrrole and polyaniline and other conducting polymer also can be used as a can be considered as a pseudo-capacitive materials because of that mechanism is only under surface reaction only happen under the conducting polymers as well. Say for example, if you have a conducting polymer, undoped conducting polymer here, once it is charged, if it is a p-type polymer, how that the double layer or that electrolyte ions, the counter ions gets diffused in that materials, in the chains of the polymer chains. In the case of the N-type, you look at here, this is a polymer, before charging, so this is electrolyte solutions, and if this is a polymer coated on that electrode material, current collector. So here, look at here how that charge distribution while charging that conductive polymers, which means metal oxides and the conducting polymers always considered as pseudo-capacitive materials, and some metal oxides, it is not at all cases. Sometimes it can also show double layer formation. That depends on for conducting polymers. That depends on the pH of your electrolyte medium. So, for example, sometimes if you use a polypyrrole even in base electrolyte, it can show only don't show any pseudo behavior like this. It can show double layer behavior. So that depends on that. That how diffuse or how that electrolyte can, the counter ions can interact with the electrode surface of your active materials. And of course, so that's what the electrochemical. What are the materials can be used as electric can perform as electric double layer formation, and what type of materials can be used as a pseudo-capacitor. What is the basic difference between the pseudo-capacitor and the double layer capacitor? So basically, the double layer capacitor can have a high voltage operation. Say for example, if you use a carbon material, you can go up to 1 volt. In case if you use a particular metal oxide, you cannot go 0 to 1 volt. So that because it is a pseudo behavior, it is based on the redox reaction. That is that potential of that electrode defined by that redox reaction. That will happen within the defined potential window. Of course, that should be happen at the particular potential, but in case of the surface reaction, we may have a broader potential, which means a broader peak like this actually. So this is what the ideal capacitor how look like, that the charge and discharge, and this is what ideal pseudo capacitive behavior. In this pseudo capacitive materials. Of course, look at here. This is that A B region. There will be a AA formation also in the pseudo capacitor, but sometimes it will be negligible when compared to the charge stored using the pseudo capacitive behavior. And another thing, it is infinitely reversible, that is EDLC capacitors, I mean electrostatic or AA capacitors, but in the case of pseudo capacitor, the capacitance, I mean, it is highly reversible. And high has a state of charge. Both have self indication of the state of charge, and that the capacitance is not constant with the voltage. This is very important factor here where we made a mistake while describing our results. So where we cannot describe this is a capacitive behavior, or where it is a capacitance behavior. The capacitance is constant with the voltage, but here the capacitance is not constant with the voltage in the case of pseudo capacitive behavior because of the pseudo mechanism. I will explain you clearly where we have to mention it is a capacitance, where it is mentioned as a capacitance. Okay, now we had materials in hand, EDLC materials, which means plenty of carbonaceous materials and plenty of metal oxides. Simply what we do once we join a PhD or we have been started to our research careers, we can focus on materials. We may have enormous materials like metal oxides, transient metal oxides, or different phases of metal oxides, and different carbonation material. You have plenty of materials with your hands, like graphene oxide, graphene CNT composites, or activated carbon CNT composites. So how we can determine the specific characteristics of that materials, particularly in supercapacitor cases. So if you have a material, say for example MnO2, or if you have any activated carbon, how we can determine the specific characteristics of that materials? So for electrochemical specific characteristics particularly, in that case, what we can do, so we can use electrochemical oxidation. Likely, if you have in your laboratory either electrochemical oxidation, likely CH instrument or chrome or solotron, there are plenty of electrochemical oxidation, or you can develop your own electrochemical oxidation. So if you have that skills, so you can do based on that. Using that electrochemical oxidation, we can define the specific characteristics of the electrode materials using the 3-electrode system basically. So what is nothing but a 3-electrode system? So simply what we can do, we can follow our seniors, or we can follow some literature. So okay, of course, in the literature they define everything perfect, no matter we can follow the literature, there won't be any error. Of course, when we do practically, in ideal case, everything is perfect. But when we do practically, there will be so much of errors. So each and every errors can accountable in the performance. So in that case, how we can test that, or we can form the 3-electrode system. So this 3-electrode system, not the actual device of your electrode materials. So 3-electrode system, which always used to determine the specific characteristics of the electrode materials. I will tell you what are the specific characteristics can be measured using the 3-electrode system for the supercapacitors. So in the case of 3-electrode system, say for example, this is the 3-electrode system. So this is a working electrode, and another one is a counter electrode, and another one is a reference electrode. So for example, our material, if you have your own material always will be the working electrode. So I will tell you how to prepare that electrode materials, and it will be varied based person to person, or depends on the research groups or how they are using that working electrode preparation. Say for example, working electrode. So if you have if you consider any metal as a working electrode. Say if you have any metal as a working electrode, see here. So here that metal electrode is the pH dependent. So for example, hydrogen under oxygen evolution under the hydrogen evolution reactions. Say for example, if you use a PT metal electrode, that oxygen evolution, so which is usually at 0.7 volt, the hydrogen evolution reaction. In the case of classic argon, it will be that oxygen evolution apparatus above 1 volt, and here the hydrogen evolution nearly 1 volt. So which means, so we can determine that working electrode potential using this 3-electrode system. But for a particular electrolyte, say if you have only metal electrode, so if you immerse within the electrolyte system, you cannot measure the working electrode potential of your working electrode. In that case, so you may need some reference electrode. With respect to the reference electrode, we can define the potential window of your potential window of your electrode material. So in this case, This is very, very important. So if you have a carbon active electrode materials, you cannot use directly that bulk material as a working electrode. You have to process it and you have to fix it any current collectors. Right. So in that case, the selection of current collector is also very, very important. Say for example, if you have activated material, see this is your active metal oxide coated on the platinum means, you see here, so that hydrogen evolution occurred at 0.7 volt and minus 0.7 volt, and of course the hydrogen oxygen evolution also occurred very faster than the carbon based substrate. So that is very, very important selection of current collector. Say many of the cases we may use nickel foam as a current collector. If you can use so what will happen if you use activated carbon as your active material. If you use nickel foam as nickel foam as current collector, if you punch your activating material, activated carbon in the nickel foam, what will happen? Nickel foam have active, electrochemically well active, and then the action evolution will be occur very fast, nearly 0.5, 0.35 volt versus RHE. So which means it is very difficult to find the potential window of your active material. So that is very, very important. So the selection of current collector and that is also depends on the electrolyte medium. So in order to determine the active material potential, so we cannot simply use only working electrode immersed in the electrolyte condition. We cannot determine the potential. So we need the reference. So at the same time, that the impedance should be very high between that electrode and the reference electrode, which means the reference electrode always not allowed to pass any current, because the reference potential always to be stable. Sometimes it is accessible. Some nano current may always pass through it. We can't avoid it, and of course. It should be non-polarizable, and sometimes very limited amount of current can be flow through it. We cannot allow it. We cannot control it. So at the same time, even that current is flow through it, that potential of the reference electrode always should be stable. So if it is stable only, we can determine the potential window of our working electrode. And at the same time, the next one, that current. So when that oxidation, reduction or EDFC formation occurred, there is a current train or gain by the working electrode. So that current flow through that the system. So what will happen? That the potential will be vary. So that current trained or gained by the working electrode should be captured by some other active material. So that we used counter electrode. So what will happen? The role of counter electrode, that the current trained or gained, that depends on the oxidation reduction process. So if it is an oxidation reduction that the current can gain on drain, so it depends on the electrochemical reaction. That current can be gained by the counter electrode. So that all the current can be gained by the counter electrode. So that's why that the counter electrode area always should be very high. You should always try to capture or try the gain or whichever the current detached from that working electrode. So that's why so it is always desirable to use high surface area counter electrode. Of course, sometimes, so maybe your electrode materials maybe gets oxidized easily, means we may use some inert gases, so using such a setup. But normally lab scale, it is always difficult to have such a lab scale setups like this, ideal setups. So we may use a simple setup. So sometimes what we need to consider, we have to consider the fact, or visibly you have to find any air bubbles that comes to your electrode. So you have to which means you have to test your electrode potential within that the gas formation potential window. Of course, the hydrogen evolution, the oxygen evolution, or HER, that is oxygen, that air bubbles is important, but here in storage that is very bad. So we have to operate the cell potential. So within that oxygen evolution potential. Okay, now come to that supercapacitor part. So what kind of specific capacitor can be determined using the three electrode system? You see that the potential window of your electrode and how much the charges can be stored, the specific capacitance of your electrode materials, and equivalent series resistance, that is the ESR of your material. Of course, that is based on the interface phenomena and the cycle life of the system. I'm going to give one of I will give each one explain. one examples for how to determine the potential window or specific capacitance, cycle life, and equivalent series resistance. Of course, how to prepare the working electrode for the bulk material. So you have a metal oxide powder or activated carbon powder. So simple activated carbon as metal oxide mostly have that poor conductivity, so that the resistivity will be very high. So it is very difficult to get more power. So that we have to improve that the power density. So we have to minimize that. We have to increase the conductivity. So in that case, we can add additive conductive additives such as conductive carbon. You can put it material raw material powder and certain ratio 80-20 or 80-70 is 20 or 10 percentage of the binder. Say for example, if you use your active material and put that conducting material as much as needed, and then if you use some kind of binder, otherwise you can't attach your material with that current collecting substrate. Of course, I always prefer the carbon-based substrate because of that larger potential. So than any other metal-based current collectors. So if you use the prepared materials, so you have to coat it and dry that materials, and you can use it. So at least you have to load 3 mg of active materials. So if you use less than, let's say for example, I use 0.1 mg, 0.2 mg means it is meaningless. Of course, you may have a better performance. You can show some beautiful CV or electrical performance, but that values that the capacitance value may not be reliable. So at least you have a standard protocol. At least you should have 3 mg active material in your active electrode material, active electrode materials in that working electrodes. Of course, we have prepared the working electrode. You may have using the platinum as a counter electrode, probably the platinum mesh or platinum larger platinum area. And the reference electrode, we have to choose the reference electrode based on the counter ions which you used in the electrolyte. Say for example, if you use H2O sulfur, you have to use mercury sulfate. Or some cases, if you for a typical lab environment, we may have a standard column electrode which use saturated KCl or 0.1 molar or 1 molar KCl used in the reference electrode. Anyhow, the reference electrode potential will be more stable in that case. Of course, each and every time we have to calibrate the working electrode potential. There are some steps involved in how to calibrate the reference electrode potential, standardize the reference electrode potential. You can Google it and you can easily find out how to standardize the reference potential every time. Otherwise, there will be error in that measured potential. Okay, now come to the potential measurement. So, how to determine the potential window of your electrode materials? Say I have activated carbon. I am going to determine the electrochemical potential window of my electrode potential. So that is called an electrochemical process, nothing but a cyclic voltammetry. If you connect your material in the 3 electrode system, so you have to measure the potential window. Of course, above 1.2 or 1.23, there will be hydrogen evolution, and of course, even the positive side 1.2 volt, above 1.2 volt or above 1 volt, there will be oxygen evolution. So in this case, we can find the CV curve within this range. Of course, if you even if you use any metal oxide in aqueous electrolyte medium, you have a CV curve like this. So see, look at here. Here, if you find this comp, even in the oxygen evolution, and this is hydrogen evolution, which means that electrolytes start to decompose. So we don't want to allow that electrolytes start to decompose. So better we have to fix the potential window within this decomposition region. So which means that in this case you see here you have to fix the electrochemical potential window between 0.9 to 0.9. That will be the more safer side, that won't allow any oxygen evolution as well as the hydrogen evolution formation. Of course, when you use the CV curve, if you're going to present it, it is always important to normalize. If you compare 3 to 4 electrode materials, you have to use a normalized current density. Say for example, that as measured CV curve can use the potential window as well as the current. So if you divided your active mass by your active mass, say for example, if you loaded 3 mg of your active material in the electrode, if you divide it by the current getting in the y-axis, so that can give the normalized current, or that is nothing but a current density. And in the case of y-axis, if it is a 3 electrode system, as long as if you are using a 3 electrode system, you are testing your materials, working electrodes potential. So your materials potential window, so that the work done happened only within the electrode, so that we always use, so that name is called as a potential. So sometimes what we made a mistake, so we can use voltage. We can't use this voltage here. It should always be potential, because we are doing the work done. That work done happen only at within the electrode only. If you are combining 2 electrodes only, you can go for that. You can mention that is potential, this voltage. So this is a major mistake. Usually I can even myself sometimes early stage I also used to make it, and even in the literature we can usually used to find kind of mistakes when you use a two electrode system. People were used to potential, and sometimes they used potential. You have to, they mention potential even in the three electrode system. So actually voltage in the three electrode system. So we should use, we have to be careful in the three electrode system. We have to use only the potential. And of course, I have the EDLC, I mean, I have the CV curve, and in this case, so I don't know whether I have a different variety of materials, likely pseudocapacitor material and EDLC material, as I explained earlier. So how that the CV curve can look like for EDLC? Of course, the blue line of the curve shows the EDLC. Of course, the red line shows the ideal curve for the electric double layer formation. In the practical, we cannot get like this, but practical we may have like this, even better like this. Of course, sometimes some cases we have. I also found kind of nearly ideal cases. Maybe some like little resistance, and we may have nearly a kind of double layer. If you work more precisely, if you fix a more precise three electrode system, you can nearly have any activated carbon in a KOH medium. You can have exactly double layer as like it in the ideal case. Of course, but in the most of the practical ways, we can have the double layer formation like this. And in the case of pseudo capacitor behavior, you can have that pseudo capacitor is due to the reaction, oxidation reduction. It can show us that behavior like this, oxidation and reduction. And say for example, so you measure the potential window. So now you know 0 to 0.8 volt will be the potential window of my electrode. Say for example, EDL, carbon material. So what you can do, you have to measure. You can vary the scan rate, which means that the rate of reaction of the electrode, which means the diffraction phenomena can happen at a faster rate. So you can enhance the scan rate from 5, 20, 50. So what will happen when you increase that far? I mean that the scan rate, that peak current density will be increased. The current of the current of the curve will be increased. So which means that the charge transfer path will be reduced, then that current will be enhanced. So okay, now we have that CV curve at a different scan rate. How we can determine the capacitance from the CV curve? So let's say for this is the standard formula, IDV divided by 2 Vs over delta V. So here this integral IDV can give that the area under the curve. So which means you can integrate that area under the curve, the CV curve. So which is can give that IDV. So when you integrate, that can give the total area of the electrode. So that you are putting 2, you can give only the charge part or discharge part. So which means if you are giving the capacitance mean, it is a discharge capacity or charge capacity. So then this is what the scan rate. So what scan rate the CV curve is recorded, and this is the potential window. This is 0 to 1 volt means that is the 1 minus 0 of then you get that electrode potential will be 0. Electrode potential will be 1. So then you can determine the specific capacitance of the electrode. In case if you divided the capacitance by your active material, then this is the specific gravimetric capacitance. If you divide it by the area of the electrode by that capacitance value, then that is the areal capacitance. If you use that volume, then that is the volumetric capacitance. Say for example, you can directly plot the kind of capacitance versus voltage plot. Simply if you have the current as like here, and this is a scan rate. So here you can divide that current divided by the scan rate, you can have the specific capacitance versus voltage plot. Of course, this is a 2 electrode system. It is a 2 electrode active carbon based system. That's why they put the voltage. In fact, even in the 2 electrode system, we don't want to run -2 to +2. Previously they mentioned, and even this is what this is. You can see that detailed information in this reference as well. So this is how we can determine the specific capacitance from the CV curve from the 3 electrode system. Of course, as I mentioned, the EDLC behavior it can look like, and the pseudo capacitive behavior will look like. In most of the cases, in pseudo capacitor also, we can get the intermediate stage between these. And if you have more sharp peaks, it can be a capacitive type. This is nothing but of a battery type versus a potential during the scanning. And this part, the charge part, I will explain you later. As I mentioned, in the EDLC, the potential will be linearly vary with the time. And in the case of pseudo-capacitive, it may not be linear, there may be a fluctuation in that discharge curve. But in the case of battery type, the battery type is voltage independent, which means the charge storage is voltage independent. So here you can charge the you can store the charges at a particular potential. You see here, you can in the battery always you can have a plateau region. At that plateau region, that all the charges can be accumulated, which means the charges can store. But in the pseudo-capacitive and the electric double layer, you cannot find such a behavior. If fortunately or unfortunately, if you have such a behavior, you cannot calculate the capacity. You should calculate the capacitance. Since the capacitance is voltage dependent, the capacity is voltage independent. This is a very major critical part in that electrochemical capacitor behavior. So I can show you, so in case if you have a CD curve and from the CD curve, I don't know, visually you can find whether the oxidation peaks comes okay. Now, so that's what I mentioned. Maybe sometimes the pseudo-capacitive peak also, maybe you can have such a phenomena, you can measure, you can, we can conclude this is pseudo-capacitive behavior, but in actual case it may not be. So that we have to define, so we have to more accurately. So in that case, what we can have, we have the peak current and we have the scan rate. These are the known data. If you plot the curve between the peak current as well as the scan rate, so square root of the scan rate, what will happen? So you may have some straight line. So usually you will have a number of, you have to test your 3D system at a different scan rate, number of scan rates, and each number of scan rate you may have a scan rate as well as that current density, peak current density. In that case, what you can have so if you fit that, you can have the slope value. If you have the slope, which means that I equal to A mu power P. So if you have the slope, if the slope value is 0.5, exactly 0.5, it is a diffusion controlled electrochemical process. It is nearly a battery type. If you find the slope is 0.5, exactly you can accurately, you can mention that that is a battery type electrode. If that P value which is equal to 1, which means the slope value which is 1, that is the capacitive type, which is completely that is capacitive behavior. If it is a mixed type, that is a 0.5 to 1, so it may have the mixed process, it is a diffusion as well as a capacitive. Using this relation, there is a extended formulation. You can find in literature. You can, if you feel your material is only pseudo-capacitive, as I mentioned, there will be a possibility for electric double layer also, but you should minimize the electric double layer, or you have to find how much the double layer is formation. You can use this relation, and there is a extendable relation. You can, based on that, you can determine exactly how much that charge is stored due to the pseudo-capacitive behavior as well as due to the ADLC behavior in your electrode materials. So this is always very important, whether that electrode materials is pseudo-capacitive or battery type or the ADLC behavior. Say, that is what in the CD curve. As I mentioned, you see here the charging and discharging behavior for the pseudo-capacitive as well as that EDLC behavior. You see, this is the EDLC behavior. As I mentioned, this is the EDLC behavior for the 3 electrode system. And in the case of pseudo-capacitive behavior, as I mentioned in the model which I explained in the previous slide. So, sorry. Yeah, here you see here the charge. This is not the model. So how that is the actual in a practical case, how the charge and the discharge for EDLC and pseudo-capacitive and battery type. And as like, so look at here, this is the EDLC behavior. So what we seen in the previous slide, and here is the pseudo-capacitive behavior, and this is the battery type behavior. So what we majorly made a mistake here. Some of the cases we may have such a behavior. You see here that the plateau region where the most of the charges can be stored. You have to determine how much the EDLC is electric double layer formed here, as well as how much that battery diffusion based charge is stored here. So in that case, in order to avoid such a confusion, if you find the charge discharge behavior like this, you can directly find the capacity instead of capacitance, because here the phenomena involved is that voltage independent, which means at a particular potential there are much more charges are stored, so that you have to calculate the capacity. But in this case, if you find such a relation like this, charge and discharge behavior look like this, you have to calculate this capacity value of your electrode based on the discharge time, and this is the input current, and this is the voltage difference between that electrode potential. So here in this case, if you use the electrode materials, as I mentioned, you can find the specific potential, specific capacitance of the electrode materials. In this case of linear, what you can do, you have to directly fit this discharge curve, which means the dV by dt. You can get the slope value, dV by dt slope value, then capacity value divided by, which is equal to I into 1 by slope. So which means you can multiply that input current in the, discharge current with that slope value which you are obtained when you fitting that linear curve. This is what, which means you can avoid as much as possible that misleading in your measurements. So that's what, these are all the very important factors when you're working on supercapacitors. And these are all, it may give some clear idea of what we did so far while measuring the capacitance and the capacity values. And another important factor, electrochemical impedance. So this, from this you can directly measure the ESR value, which is the AC frequency measurement spectroscopy. We can directly measure the impedance value. Most of the time, this is a typical impedance behavior what we are expecting for the supercapacitor. Say if you have the semicircular region, it is a double layer dominant. If it goes like, if it is extended, you can see that that is due to the charge transfer. Of course, if you have such a phenomena in your impedance in the practical case, this is a diffusion controlled absorption. So which means we can't get this portion if it is a battery type behavior. If it is a battery, it can have like this part only. If it is only absorption, the surface reaction, which means pseudo behavior, there will be a double layer formation, there will be a diffusion also, certain percentage, and the certain, the surface diffusion process. So which means the pseudo capacitive behavior. It all depends on the nature of the material. So which means this is a typical behavior for a 3 system of any electrochemical system. So here, if you sometimes, so to get such a typical behavior, so we have, it is very important, it is mandatory to test your electrode in a wide range of frequency. So if you say, for example, I will test it just to 40 Hz to 100 Hz, or if you test it to 40 to 1,000 Hz, means you can't get that entire phenomena. If you tested your potential, your electrode material within a wide range of frequency range, only you can have all this phenomena. You see here, this is AA domination, and this is a charge transfer phenomena and diffusion controlled. And I have the practical examples also how it look like. Say, for example, it depends on the porous nature of that. The absorption is mainly depends on the porous nature of the electrode materials. Say, for example, if you have like this the impedance behavior, so it is if it goes further like this, which means if this impedance behavior, if this low frequency spike always try to near 90 degree. If it is goes to inclined angle nearly 40 degree, means it is a weaker, absorption is weaker, but at the same time that the kinetics, flow kinetics will happen. So which means from the impedance analysis we can directly determine whether that behavior of charge storage mechanism is either absorption or resorption or diffusion based process. So or it is a mixed process. Everything can be get from the electrochemical impedance spectrum. So in this case, so say for example another case, so you see for example this is ideal supercapacitor impedance, and this is what that equivalent distributed resistance of the electrochemical capacitor in experimental case. So look at here the ESR of the ideal and as well as that the practical capacitors are same. But see the phenomena, so it's entirely different in a practical case. It shows the diffusion process as well as the surface based reactions. So these are the some of the practical examples observed in that literature. So here you look at here, this is a semicircle and diffusion and the surface reaction. So from that impedance we can directly find whether this is a diffusion process or which one is the dominated, the AA is domination or surface reaction is the domination. Of course we can find that ESR value as well as solution resistance as well as the charge transfer resistance as well. You can fit the electrochemical impedance spectroscopy with some models or softwares exactly exactly we can find the equivalent circuits, whether that circuits will be, where the solution resistance and what is the resistance and what are, how the combinations of capacitance and resistance. Apart from that, most of the cases in that most of the cases what we have in the case of like impedance, sometimes we may have that the impedance behavior goes like this. So this part, most of the cases probably many people not zooming this part, and in many cases they may be rectify this and give that they mentioned their results. But in this case, this may be the additional resistance in the interfaces. Of course, this will also due to the inductive effect which happened during the impedance measurement. Or some cases, what will happen? So here, if you have the impedance behavior, there will be some loop which goes like this. So this will also happen due to that inductive effect. So that impedance analysis can give exactly how that whether that there is an inductive role is there in your interface or not, or it is inductive role free. Then we can when you go for the fitting circuits, which means when you fit your impedance result, we can determine exactly that LC circuits or RC circuit or LCR circuits. And this is another typical model. How you so look at here, as I mentioned, it looks like a completely the double layer, ideal double layer, right? So, but here you see here there is a diffusion, so as well as the surface reaction. So, which means that depends on the material. This is completely due to the mesoporous nature. If it is a highly mesoporous, there will be a slow kinetics or slower diffusion will be occurred. That's why the impedance will be look like this. And of course, so far we have defined using the 3 electrode system the potential window and the specific charge discharge, the charge storage capacitance values, and the electrochemical impedance behavior. And another important factor is the cycle life. So the cycle life of our active material is also very, very important. So that cycle life is it depends on the material structure or material nature. If it is a EDLC, no matter you can even go up to irrespective of the electrolyte anions or cations. So you can run your system more than 1 lakh cycles. But in practical cases, it is difficult. In 3 electrode system, we cannot measure, and mostly people will stop up to 10,000 cycles. That depends on the person to person. If you think it is a 5 cycle, 5,000 cycles is enough, 10,000 cycles is enough, that should be okay. But when you go for a practical application, when you go for a prototype, we have to evaluate that cycle life, at least 10,000 cycle, how it will be look like. Say for example, the cycle life of that system, electrode materials, it depends on the counter ions which we used. It depends on the electrolyte medium. Say for example, if it is a composite electrode, so say for example, even up to 10,000 cycles. So look at here, based on with respect to the counter ions, that the cycle life, there is a huge variation in that capacitance retention. See here, there are almost 20% of capacity retention will vary the counter ions. So that is a very, very important factor, the choosing of electrolyte. So which electrolyte can have the better cycle for our material. So it is a more specific, it is a it depends on the electrode materials. For that particular electrolyte, that the cycle life is more specific, the electrolyte specific. So in this case, for example, if it is used alkaline cations, lithium, sodium, potassium, or some H plus. So here in aqueous solution, the hydrated ions radius is for lithium and sodium and potassium and H plus. That's why. So for example, KOH is most of the cases is preferred, and because of the hydrated radius is very, very less, so that will give a better cycle life than any other system. This one is I'm just giving for comparison purpose. If you are varying the counter ions, how that cycle life performance of your electrode will vary. Okay, this is all about the cycle. These are all about the 3 electrode system. Okay, now I am very clear. I have ADLC carbonization materials, so ADLC which has ADLC formation, and another type of materials, that is pseudo capacitive material, or other type of materials, the battery electrode materials. It is completely diffuse and paste materials. And so I have exactly defined my potential window. I know the specific capacity, and I know the cycle life of my material, and I know the electrochemical ESR value of my material. So already I know all of the specific characteristics of our material. So from the 3 electrode system, we can only determine the specific characteristics of the material. That 3 electrode system, it's not as actual device. So what we are going to see is an actual device. Okay, now I have only electrode EDLC based material, another pseudo capacitive materials. How I can make the device? you can play with that material, you can play with the combination of materials. You may have both sides, so positive and negative electrodes as a EDLC material. You say, for example, I have a different combination, I will explain to you. Asymmetric devices. If you use a different mechanism involved in the electrode materials, say for example, if you use a EDLC material, likely carbonation materials in that positive electrode, if you use any pseudocapacitor, likely MnO2 as a pseudocapacitor material in the negative side, you can see the positive and negative are a different storage mechanism, then it is called asymmetric device. If you can either way you can vary the combination. That is depends on the potential window of your material. Say for example, in the positive potential, it has a 1 volt, it is a 0.8 volt. Yes, sir.
Sorry for the interruption. The time is over 1 hour. So
probably next 10 minutes I will wind up. Only one system I will explain. And so these are all the different combination of either asymmetric device, EDLC and pseudocapacitor. And if it is a hybrid means you should use one battery type and then EDLC or pseudocapacitor and that battery type electrode. So these are all the different types of electrode materials. Of course, these are how we can make that based on that. So how we can calculate the specific capacitance in the different formulas as I mentioned earlier. Of course, in the case of two electrode system, so we have to there is a AA formation in each electrode. If you have positive electrode and a negative electrode, say here positive and negative, each electrode have a AA formation. So here 1 by C1 plus 1 by C2, so that only, so we are calculating the specific electrode capacitance 2 into cell capacitance. So that specific electrode, if you are using the both electrode mass in the actual device, you have to multiply by 4 and you can get that actual capacitance of that specific electrode. And of course, these are all the materials you can play around. For example, if you are choosing material, the manganese oxide, that has a different structure. Each and every structure has a different phenomena. So that is a charge storage values also differ in different electrolyte medium for the manganese oxides. And you can play around certain morphologies also based on that material synthesis procedure. You can play with that. And as I mentioned, this is activated carbon, and I am going to only give one example as the time is already over. I'm sorry for that. So here this is I'm going to combine this AA material activated carbon and this is the manganese oxide pseudocapacitor behavior. And this is a asymmetric combination, and how this is the EDLC and the pseudocapacitor behavior of the material. Look at here, so that the pseudocapacitor behavior, this is a potential window. So nearly up to 1.7 volt, there is no action evolution. So here, this is what the pseudocapacitor behavior of the actual two electrode system. So you have to put volt, and here it is a voltage. So this is a CV curve and a charge charge. As I mentioned, all the formulas I was given in the 3 electrode system. So you have to use all the formulas. You can find the CV capacitance value from the CV curves, and you have to determine the charge capacitance value from the 2 electrode systems. So you can vary the different current density based on the combination. So we use the conducting material as well as your active material. You can enhance the current density of your active materials. Say for example, these are all the actual capacitance value for some of my devices. Of course, the cycle life, so far I have tested 1 lakh cycles, but the capacitor intensity is somehow okay. This is 25% of loss, but the cooling efficiency is at 99%. That is very, very important. Of course, many cases we made a mistake. After testing the 3 electrode system, we may go for the energy and power relation. That is nothing but a Ragon plot. Please don't do that. Ragon plot, don't plot any Ragon plot for the 3 electrode system. That is a specific characteristics. Only actual device, only you can measure the energy and the power density. And based on that energy and power density, you can plot that plot. Then that is nothing but a Ragon plot. It can give the direct relation how much the energy and the power which your device can show. This is another example for the asymmetric case, and this is how it will look like, and how we can optimize the potential window, and how the symmetry, the impedance as well as the other characteristics will look like. And another important phenomenon, the leakage current, as I mentioned earlier in the previous slide when the comparison between the battery and supercapacitor, that is very, very important, that the leakage current that can be controlled based on the geometry of the device. Say for example, how we can measure the leakage current after completely charged, fully charging your device, just leave it in the open circuit potential for about 10 hours or 20 hours. Then you have to record the current, how much it is leaked from the device. Then plot the voltage versus time as well as the current between the time. You can find such a plot, how much the leakage current. Of course, here it is a microampere. Usually for capacitor it is in the range. In fact, if it is a nano range, that should also find. That is depends on the materials and how we are packaging your device. That is very important. And the different kind of flexible devices. You can go around, you can play around that engineering aspect, you can play with that flexible, twistable, flexible, then prototypes, models, you can play around that. And these are all the prototypes which we can use if it is going for electric hybrid vehicles. You can play around with something. It is not a typical floating system what we are using the lab scale. That is something that is engineering package. The packaging is entirely different. I used to making tri-mosses to making the supercapacitor. This is what the 10 volt super 60 farad supercapacitor. Of course, you can test it at any shear conditions of such a device. These are all some of the comparison of such a some of the pseudo capacitive materials, likely, I mean, some of the commercial materials likely Maxwell and Niscap and Skeleton, and some of the materials which are commercially available. And of course, I am trying to get always high energy and power densities. These are all some of the applications where people are using. And this is the first board which is used only fully by supercapacitor in France. But this is in China. This is a workstation where the process charged. It is 2015 in China. Within 10 seconds, that the whole system is charged. Just imagine that how superior that supercapacitor we're using in the applications. And this is some other applications and other approaches, strategies. So what you can, where you can play around with the materials for enhancers, charge storages. You can mix, you can play with that material synthesis, likely make composites. Three-phase metal, likely activated carbon metal oxide composite, activated carbon graphene metal oxide composites. Likely you can play around the materials so for enhance the capacity and everything. And this is a standard protocol which I always use to define better capacitance, better performance of the supercapacitor. If it is in an aqueous medium, so 6 cell capacitance at least should be 80 farad per gram, 1 ampere per gram. The ESR always should be less than 100 milliohm. Cycle life at least 10,000 cycles, or at least I always try to get 1 lakh cycles for a prototype. And at least the cell voltage should be 1.4 volt for a single cell. And liquid current, if it is possible, 9 ampere also fine. And self discharge potential 30% should be even after a few days. Operating temperature should be 82. Until up to 80 degrees Celsius when using that course. Of course, I used to get the good performance even up to 80 degrees Celsius while using that course. My area of expertise, as I mentioned earlier, and Dr. Murugas was explained, during the introduction. So I had a battery, supercapacitors, and hybrid capacitor, and of course the flow battery, which used for high energy storage applications. Finally, I acknowledge that the funding which I got it, I awarded for the Commercial Fellow through SIRB, Science Engineering Research Board under the DST. And of course, CSIR Secretary, which allowing to implement my Ramanujan Fellow. And I also thank my director for allowing giving the facilities, and Dr. Raghupathi is giving the laboratory facilities for running my Ramanujan Fellowship project. And of course, I thank particularly Dr. Ramadas and Dr. Murugas giving me an wonderful opportunity to share my thoughts and giving,
Thank you.
ideas to getting better supercapacitor performance. And of course, finally, the Sathyabama Institute of Science and Technology for giving that excellent opportunity. Thank you.
Thank you, Doctor. Thank you very much for the excellent talk with the highly informative about the supercapacitor, the encoding, fabrication methodology, and the evaluation of the parameters, etc. And once again, welcome to Doctor. Actually, we don't have that much time because the time is already over 11 o'clock. So if
I am ready to answer for people are asking, and in fact you can share my email IDs. Share my email ID. If they need, you can write. Then I can have better discussion with them.
Surely. So participant may discuss with Dr. Rolanathan, maybe through email or some. If you get some opportunity, you can go to Sigri and you can discuss it. And once again, I request the participant to fill the feedback form and submit it as before leave. Again, I remember to participant about the next and the last session of the webinar today. It will be started in the evening at 4 p.m. Once again,